In the previous video, Sheldon claims that the force required to push the box up the stairs is exactly half the force required to pick up the box. Is he right? Here are the possibilities, including whether or not he is making reasonable assumptions. If you haven't already watched the video, go back and watch the previous video in the playlist. When you're ready for the explanation, then continue this video. Here is a visual representation of the box on the stairs, including the angle and the force of the push of Sheldon and Leonard. First, we need to draw a Freebody diagram with all the forces acting on the box. We have the force of the push up the stairs, the force of friction opposing the motion, so pointing down the stairs, the normal force of the stairs perpendicular to the box, and the force of gravity straight down. Next, we choose a coordinate system. We'll choose the x-axis to be parallel with the stairs and the y-axis to be perpendicular to the stairs. That means that all of the forces except one are going to have only an x component or only a y component. That will make the math in the next step much easier because we won't have to resolve all of those forces into x and y components. Instead, we'll only have to resolve gravity into the x and y component. That's what we'll do next. In order to do that, we need to figure out what angle gravity makes with the x and y axes. If you look at the angle theta in the drawing, you will notice that the angle that gravity vector makes with the negative x-axis must be 90 minus theta, because the sum of the angles inside of that triangle has to equal 180 degrees. That in turn means that the angle that the gravity vector makes with the negative y-axis is the angle theta, which in our case is 30 degrees. So we're now ready to resolve the gravity vector into its x and y component. Since the y component is adjacent to the 30-degree angle, we will use cosine to find the y component, and it's mg cosine theta. The x component is opposite to the 30-degree angle, so we use sine, and that component is mg times the sine of theta in the negative x direction. Now we're ready to apply Newton's second law for the sum of the forces in the x direction. There are three forces in the x direction. We have the force of the push in the positive x direction, the x component of gravity in the negative x direction, and the force of friction, also in the negative x direction. That means we have F push minus mg sine theta minus F friction equals 0. We choose 0 for the acceleration because we want Leonard and Sheldon to push the box up the incline at a constant velocity to minimize the amount of force that they need. It takes more force to accelerate something than it does to push it at a constant speed. To solve for the force of the push, we'll add mg sine theta and the force of friction to both sides, giving us F push equals mg sine theta plus the force of friction. Plugging in 30 degrees for the angle, we get mg sine 30 plus the force of friction. The sine of 30 degrees is a half. Thus we see that the force of the push required is equal to half the weight of the box only if there's no friction. That is extremely unlikely, so Sheldon was wrong. Evidently in this case he's not as smart as he thought he was.